Hello, today we're continuing with our GCSE Physics Revision series looking at Archimedes Principle. Let's first state Archimedes Principle and then we can see what it means. Archimedes Principle says that when a body is partly or wholly submerged, it experiences an upthrust which is equal to the weight of fluid displaced. So this relates to bodies in a fluid or a liquid. So let's have a bath in which we put a fluid. Now what Archimedes' principle says is that if you put a body in that fluid, or even partly in that fluid, so partly or wholly submerged, if you do that, there will be an upthrust. The fluid itself will produce a force that pushes that body up. And that upthrust, which is a force, will equal the weight of fluid displaced. Well, what is the weight of fluid displaced? In this case, we know that there will be a certain volume of fluid displaced. The volume displaced will be the volume of the body itself. And there is a thing called density. Density is equal to mass divided by volume. Density is common for any given substance. So for example, the density of water is 1 gram per centimetre cubed. That's not in SI units, but I'm just giving you that. That's a common for water. But density is simply the relationship of the mass to the volume. The important point about that is if you know the volume of something, then you also know its mass, provided of course you know the density, because mass is equal to density times volume. So if you know the volume of something and you know its density, you also know its mass. So what we are saying is that when there is a body that is in a fluid, partly or wholly in a fluid, that body, of course, will have a force acting down, which is its weight. And that will be mg, where m is the mass of the body, and g, of course, is the gravitational force, which is 9.81 meters per second squared, unless you've been told that you can use 10 instead of 9.81. So there's a force acting down that will cause that body to go down, to sink in the fluid or the liquid. But Archimedes says there's also an upthrust, and that upthrust is equal to the weight of fluid displaced. And so you can have a situation whereby here is a body partly submerged in the fluid. This bit is below the surface, this bit is above. The total mass of this body is acting down with a force mg, and there is an upthrust which is equal to the weight of the fluid displaced. So this is the volume of fluid displaced. Obviously, you don't displace the volume that's above the waterline, you only displace the volume that's below the waterline. That's the volume of water displaced. So the mass of the water displaced, assuming the liquid is water, is going to be the density times that volume. And so the weight of fluid displaced, mg, is going to be the density times the volume times g. So we can work out the weight of fluid displaced, and we know the weight of the object itself. Now suppose those two things just happen to be equal. That means that the weight of the object, which is tending to make it sink, is going to be exactly matched by the upthrust, which is the weight of fluid displaced. If those two things are equal, there is no net force. And if there's no net force, there will be no net movement. Consequently, the object will neither go any further down nor any further up, and we call it floating. Let's consider a bath of water, and the density of water, and now I will put it in SI units. The density of water is 1,000 kilograms per meter cubed. I'm rounding, but very roughly that's the density. So every meter cubed, every cubic meter of water weighs 1,000 kilograms. That's what that tells you density-wise. And I'm going to have 1 cubic meter, so 1 meter cubed of iron. And iron, I can tell you, this is the density of water. The density of iron is equal to about 7,800 kilograms per meter cubed. And I've got 1 cubic meter of iron, and the question is, will it sink or will it float? Well, what we've got to ask ourselves is, what is the upthrust and what is the weight of iron? Well, first of all, we know that the volume of iron is 1 cubic metre, I've told you that. And I've told you what the density of iron, it's 7,800 kilograms per cubic metre. We've got 1 cubic metre, so its mass is 7,800 kilograms. So the force acting downwards, the gravitational force, and I'll put the arrow meaning that's what's pulling that iron block down, will be equal to mg, and that's going to be 7,800 kilograms times g, which I'll assume is 10. We'll have that g is 10 meters per second squared for simplicity. So the force acting down is going to be 78,000 newtons. Right, that's my downwards force. What is the upwards force when this block is completely under the water? Well, when this block is completely under the water, it will have displaced 1 cubic metre of water, because its volume is 1 cubic metre. If you put 1 cubic metre in the water, it means that where there used to be water, there is now 1 cubic metre of iron. So it is displaced 1 cubic metre of water. What is the weight of that water? Well, the weight of water is the upthrust, because the upthrust is equal to the weight of fluid displaced. And the upthrust is the upwards force. Well, firstly, what is the weight of water? Well, the volume of water that's displaced is 1 cubic metre. The density of water is 1,000 kilograms per cubic metre. So the weight of water displaced is 1,000 kilograms. So the upwards force is going to be 1,000 kilograms times g, which is 10, and that's going to give me 10,000 newtons. So in the case of this iron block, which we're putting into the water, we have got a total weight of iron which is 78,000 newtons, and that is the force that's acting down. We've got an upthrust which equals the weight of fluid displaced, in this case the weight of water displaced, and the upthrust is 10,000 newtons. 78,000 down, only 10,000 up. So the force acting down wins, it's greater than the force acting up. Consequently, that iron is going to sink because the force acting down is greater than the force acting up. Now let's suppose that instead of using iron, we use ice. Again, we're going to take 1 meter cubed of ice and we're going to put it in the water. Well, the first thing we need to know is what is the force acting down. I can tell you that the density of ice is 900, roughly, kilograms per meter cubed. And since I've got 1 meter cubed of ice and the density is 900 kilograms per meter cubed, that means that the mass of the ice is 900 kilograms. So the force acting downwards, that is the weight of the ice, is 900 kilograms times G. G we said was 10. That's going to be 9,000 newtons. So we've got 9,000 newtons acting downwards. That's the weight that is going to be coming down. But when that ice gets into the water, it will experience an upthrust, and the upthrust is equal to the weight of fluid displaced. Well, what is the volume of fluid displaced? 1 cubic metre. What is therefore the weight of fluid displaced? Well, we worked that out before. Water has a density of 1,000 kilograms per cubic metre. If a cubic metre of water is displaced, that means 1,000 kilograms of water is displaced, and therefore the weight of fluid displaced, which is equal to the upthrust, is going to be 1,000 kilograms times gravity 10, which is 10,000 newtons. That's the force acting up. So now we've got a force of 9,000 newtons acting down, but a force of 10,000 newtons acting up. The upthrust is greater than the force acting down. Consequently, if that ice is wholly submerged, the upthrust will push it up, and it will end up in a position where it is floating. Some of it will be beneath the surface, and some of it will be above the surface. So now I want to calculate how much of the ice, what proportion of the volume of ice will be beneath the surface. So here's the bath, here's the water, and here is the ice, which is floating. You'll notice some of the ice is below the waterline and some of it is above. Our question is to find out what is the proportion that's below the waterline. Well, firstly, we need to think about what are the conditions that will make it float. If it is floating, it is neither moving upwards nor is it moving downwards. It's not sinking and it's not rising. It's floating. That means that there is no net force on it, which means that the force acting down, which is the weight of the ice, must be exactly matched by the force acting up, which is the upthrust, which according to Archimedes is equal to the weight of fluid displaced. And remember, the volume of fluid displaced in this case is just the volume that's below the waterline. You don't displace water with what's above the water, you only displace the water with that bit of the ice that is below the waterline. Let's say that the total volume of the ice is V, but the volume of the ice below the waterline is V1. Okay, so the total volume, that's this whole volume here, is V, and the volume beneath the waterline is V1. So I'm essentially asking the question, what is V1 over V? In other words, what is the proportion under the water compared to the total volume? That's what I want to find. For these purposes, it doesn't matter what the volume is. It could be any volume. It could be an iceberg. Well, the first thing we want to find out is what is the total force acting down, and the total force acting down is going to be the mass of the ice times G. So force is equal to mass times G, acting downwards. But the mass, remember we had before that density equals mass over volume, consequently mass is equal to density times volume, so the force acting downwards is going to be the mass, which is the density of ice, times the volume of ice, capital V, times G. Because remember, we're talking about the mass of ice, that's the density of ice times the total volume of ice. Total volume we said was V, that's mass, times G. So that's the total force acting down. What's the total force acting up? Well, that's the upthrust, which is the weight of fluid displaced. What is the volume of fluid displaced? Well, it's V1, because that's the volume of the ice below the surface, so that's the same as the volume of water that is displaced. So the mass of fluid displaced will be the density of water times V1. That's the mass, right? Density times volume. Density of water times the volume of the water displaced, and the volume of water displaced is V1. And then of course we also have to multiply that by G to get weight. So we've now got a force acting down, which is the density of ice times the total volume of the ice times G. And we've got a force acting up, which is the upthrust, which is the weight of fluid displaced, which is the volume of water times the volume of ice beneath the water, because that's the amount of volume of water that is displaced, times G. If that object is floating, then those two equations must be equal. The force down must equal the force up, which means that rho I Vg must equal rho W V1G. The G's just cancel, so we can forget about those. And now you have, rearranging these equations, V1 over V is equal to rho I over rho W. But I told you before what rho I was. It was 900 kilograms per metre cubed. And rho water is 1,000 kilograms per metre cubed. So when you divide 900 by 1,000, you get 0.9. And that's what we wanted. And what that tells you is that 90%, 0.9 of one complete unit, 90% of the ice is beneath the surface when ice floats on water. That's what makes icebergs so dangerous, because if this is the surface of the water and you see an iceberg sticking up out of the water, what in practice that means is that 90% of that iceberg is actually submerged. And that's what the ship is going to hit. It's not just the little bit that you see above, it's the massive amount below. In that fluid, or even partly in that fluid, so partly or wholly submerged, if you do that, there will be an upthrust. The fluid itself will produce a force that pushes that body up. And that upthrust, which is a force, will equal the weight of fluid displaced. Well, what is the weight of fluid displaced? In this case, we know that there will be a certain volume of fluid displaced. The volume displaced will be the volume of the body itself. And this is equal to the weight of fluid displaced. So this relates to bodies in a fluid or a liquid. So let's have a bath in which we put a fluid. Now what Archimedes' principle says is that if you put a body in, there is a thing called density. Density is equal to mass divided by volume. Density is common for any given substance. So for example, the density of water is 1 gram per centimetre cubed. That's not in SI units, but hello. Today we're continuing with our GCSE physics revision series looking at Archimedes' Principle. Let's first state Archimedes' Principle and then we can see what it means. Archimedes' Principle says that when a body is partly or wholly submerged, it experiences an upthrust which is